In this video, we will discuss the solution to the question from 6 to 10 from exercise of chapter number 2. So let's start. Question number 6 is that in each case perform the indicated operation. So let us start solving one by one. 6a. So in C star is nothing but the set of complex numbers. Set of complex numbers without zero. And this star indicates that they are talking about C as a group under multiplication. So here we need to give the solution of this question. So we need to perform multiplication of these two complex numbers. So 7 plus 5i into negative 3 plus 2i. This is equals to 7 times of negative 3 plus 2i and plus 5i negative 3 plus 2i. Usual multiplication we perform. So 7 into 3, that is negative 21, and then 14i, and then when we multiply this we get 15i, and then plus 10i square. And note that iota square is negative 1. So this is minus 21, then 14i negative 15i. So this is minus 1i, and then this is negative 10. So this is negative 31 and minus I. So this is the answer of first part of question 6. So let us discuss the second part of this question. So in general linear group of order 2, elements has been taken from Z13. So first we know that what are the elements in Z13, and because there is no star on Z13, so it means they are talking about the additive group of Z13. So let us solve this question. So 6b part. So matrix is there 7, 4 and 1, 5. So let A equals to 7, 4 and 1, 5. So we need to find A determinant of A. That is determinant of A. So let me check once again. The entries are same. Yes, they are same. So elements are elements are from Z13, and we know that in Z13 the elements are 0, 1, 2, 3 up to 12. In general, in Zn we have element 0, 1, 2 dot dot up to n minus 1. This is in general case. So let us find out determinant of A. This is equals to, usual way we find, we multiply 7 into 5, but because the elements are from Z13, so we use the operation of this set, of this group. So 7 into 5 under modulo multiplication 13, and minus then 1 into 4. So 1 into 4. So this is equals to 7 into 5, that is 35, and of course 35 when divided by 13, 35 when divided by 13 leaves remainder 13 2 times. We can go up to 2 times, that is 26 and 26, and then remainder is 9. Or else we can say 35 is congruent modulo to 9 modulo 13, because 13 divides 35 minus 9. 35 minus 9, that is 26, of course. So 13 divides 26. So that's why 35, using the congruence relation, 35 is congruent to 9 modulo 30. So here we can write directly 9 minus, this is 4. Now 9 plus, because there is no subtraction kind of thing in this group and the element are from this group only, so we can write either we can directly write also this is equals to 5, but thing is that what is going on internally, we can see here, this addition is nothing but modulo 30 addition. So minus 4 is congruent to how much we need to subtract from negative 4 so that 13 divides it completely. So this element is 9 modulo 13, because 13 divides minus 4 minus 9, that is 13 divides minus 13, and this is all true. So we can replace 9 and this thing by 9 modulo 13. So this is 18, and 18 is congruent modulo 13 to 5, because when we subtract 5 from 18 we get 13, and 13 divides 5, so we can write here 5. So finally determinant of A is 5. So this is the answer of the B part of question number 6. So what we see here, we can write directly also, but thing is that we need to know what is going on behind the scene. So let us see the next question. So next question is we need to find the inverse of this one and entries from the set of real number. Of course, general linear group of 2 by 2 order, and inverse we need to find the inverse of this 6, 3 and 8, 2. 6, 3 and 8, 2. So let's see 6, C. So let A equals to 6, 3, 8, 2. This is the matrix we are given. So we need to find A inverse. This is the question. So we know that if B equals to A, B, C and D, then its inverse is given by 1 over determinant of B, and just to set this D, A, and put negative sign with minus with B and C. So this is the A inverse. So using this result, we can write A inverse equals to, now we need to find a determinant of A. So first determinant of A is this, calculate determinant of A. Determinant of A usual, because the entries are from the set of real number. So 6 into 2, that is 12 minus 24, that is minus 12. So 1 upon 12, and then just to say is 2 and 6, and here negative 3 and negative 8. So this is the answer of C part. So let us see the last part of this question. So now entries are from Z7. So 2, 1 and 1, 3. Now consider the question 6D. The question is that we need to find the inverse of A, where A is a matrix and entries from Z7. So we know that the additive group Z7 has the element 0, 1, 2 up to 6. So to find the A inverse, we need to first find what is the determinant of A. So determinant of A equals to 2 into 3 minus 1 into 1. This is equals to 6 minus 1. Either we can write directly, or else we can write 6 plus, this is a minus 1, and of course we all know that negative 1 is congruent to 6 modulo 7. So we can write here 6 plus 6, here 7. 6 plus 6, that is equals to 12, and 12 when divided by 7 leaves remainder 5. So both are the same. Either we kept it directly or like this. This is the behind the scene what we have seen. So A inverse. A inverse is what? 1 upon determinant of A, that is 5, and then he said these two, 3 and 2. So 3 is here, 2 is here, and just make negative these two elements. Now, as previously we have seen, negative 1 is congruent to 6 modulo 7. This is we are doing because there is no negative element in this one, and A has the element from Z7 only. So we can write 1 upon 5 and 3. Let's replace negative 1 by 6, and then 6, then here 2. Now we can write 5 inverse and 3, 6, 6 and 2. What is a 5 inverse? When we talk about the 5 inverse, because we are going to multiply with 5 inverse with all elements of this matrix, so we need to find multiplicative inverse. So multiplicative inverse of 5 is multiplicative of 5 inverse 5 is what will be 3. 5 3, that is 15, and 15 is congruent to 1 modulo 7. So we can write 3, 3, 6, 6 and 2. So let us multiply, and 3 into 3, 9, but 9 is greater than 7. So divide it by 7. So there are two operations simultaneously going on. One is multiplication modulo 7 and addition modulo 7. When we consider multiplication modulo 7, we exclude 0, and when we consider addition modulo 7, we include 0, all elements of this set. So 3 into 3, that is 9. 9 divided by 7 leaves the remainder 2, and 3 into 6, 18. 18 divided by 7, this will give us 4, and then again 6, 18, that is 4, and then 6. So this is the required result, A inverse. Okay, fine. So let us consider the next question. Question number 7. Give the reason, any two reasons, why the set of odd integers under addition is not a group. So answer to question number 7. So let us write first set of all integers, odd integers. So Z, let us write O here. This is equals to plus minus 1 plus minus 3 and so on, like this. Set of all odd integers they are talking about. So here one thing is there. First, 0 is not there, so no additive, because they are talking about addition, so no additive identity. Two reasons. And second reason is operation is not closed. That is 1 plus 1, this is equals to 2. Set sum of 2. Let us take any two integers numbers from this set. So this 2 and this 2 is doesn't belongs to 0. So this is not closed. Not closed. So two reasons are there. So let us consider question number 8. Answer to question number 8. So list of elements of U20. So let us recall what is UN. UN is the set of elements of natural number which are relatively prime to n and less than n. So U20. What are the elements in this one? So 1, of course. 2 not, because 2 and 2 divides 20. 3 can be there. 4 cannot be there. 5 cannot be there. 6 cannot be there. 7 can be there because 7 and 20, their greatest common divisor is 1. Then 8 cannot be there. What about 9? 9 and 20. So 9 should be there. And then 10 cannot be there. Then 11 can be there. And then 12 cannot be there. 13, no 14, no 15, 16, no. And then 17. And then 18 cannot be there. And then 19. So these are the elements in Q20. We need to find the element such that greatest common divisor of 20 and n equals to 1. So we can take one element. 1, that is 1. Then 7, because 7 is prime number. So only 2 divisors, 7 and 1. Only 2 positive divisors, precisely, if we say. Then 9, so 20 and 9, there is nothing common. Of course, this is it has 2 divisors, 1, 3 and 3 square. But none of these divides 20. So similarly 11, 13, 17 and 19. So these are the elements in say U20. So let us consider next question. Prove that answer 9. Prove that 1, 2, 3 under multiplication modulo 4 is not a group. So what are the basic requirements for a group? First thing, it should be closed, inverse, associative, and identity. Of course, it is visible there. Identity element is 1 because when they are talking about multiplication modulo 4. So when we multiply by 1 any element, in any element, this will give the same element. So identity is there. What about associativity is also there because this set 1, 2 and 3 they are subset of the set of integers. So set of integers. So associativity, we know that associativity holds there. So, next we consider let us talk about the inverse. 1 into 1, that is 1, of course. So 2 into 3 equals to 6. And when we divide by 4, this will leave remainder 2. So from here, 2 and 3, they are not inverse of each other. So what is the chance? Chance is there, 2 must be self-inverse and 3. So 2 square, now 2 square is 4, and when divided by 4, it will give us 0, but 0 not belongs to this set 1, 2 and 3. Also 3 square, that is 9, and 9 when divided by 4 give us 1. So of course 1 belongs to this set 1, 2, 3. So no closure property doesn't hold here. At least one reason we got not closed. Not closed because 2 into 2 is equals to 0. 0 is not member of 1, 2 and 3. The second part, that is we need to prove that the set 1, 2, 3 and 4 under multiplication modulo 5 is a group. So let us see. The set is given 1, 2, 3 and 4. And this is nothing but Z5. And we need to prove that Z5 under multiplication modulo 5 is a course, we can for a collectible to prove this one. This will tell everything. 1, 2, 3, 4. 1, 2, 3, and 4. Then multiply this 1, 2, 3, and 4. So 2, 3, and 4. These are easy. So 2 into 2, 4, and 4 is less than 5. So we can write 2 into 3, 6. 6 when divided by 5 leaves remainder 1. So 2 into 4, 8. 8 divided by 5 leaves remainder 3. So 3 into 2, that is 1. 6 divided by 5, this leaves remainder 1. And then 3 into 3, 9. And divided by 5 leaves remainder 4. And here similarly 2. So 4 into 2, 8. Divided by 5 leaves remainder 3. And then 4 into 3, that is 12. 12 divided by 5 leaves remainder 2. And of course 4 into 4, 16 divided by 5 leaves remainder 1. So this itself proves that 1 is identity. 1 identity. And of course associativity we can see just like suppose 2 into if we need to verify 2 into 3 into 4. So this is what is this one? And 2 into 3 and then 4. So we need to see. So let us simplify bracket. This and just giving an example. 3 into 4, 12. 12 divided by 5. 3 into 4, 12. 12 divided by 5, 2. And then 2 is now this becomes 2. 2 multiplied by 2. 2 multiplied by 2. That is 4. So this gives 4. 2 into 3. So 2 into 3, that is 6. And this is nothing but 1. And then 1 into 4, that is equals to 4. So both are the same. Similarly, we can verify other pairs also. So associativity also holds. Identity is there. Of course, when we apply this operation, multiplication modulo 5, every element in each row and each column belongs to this set. So this is closed also. About inverse, 1 is inverse of 1 itself. Here 2 is inverse of 3. Here 3 is inverse of 2, of course, and 4 is inverse of self. So this is the thing. 1 is inverse of 1 and 2 is inverse of 3 and 4 is inverse of 4. So every element, they are the self-inverse and they are inverse of each other. So this is the solution of this. Next question, let us consider question number 10. So we need to find here, this refers to the example number 9 of your textbook, is non-abelian by exhibiting a pair of matrices. So we need to find some pair of matrices and then multiply them to show that they are BA and AB are not equal. So let us take matrix, consider matrix 0, 1, 2, 1, and then 1, 1, 0, and 2. So AB, we can find AB 0, 1, and 2, 1, and then 1, 0, 1, 2. So this is equals to R into C, 0, and then 1. So here 1, and then 0, and 2. That is 2. And then consider second row, 2, and then 1. That is 3. And similarly 0 and plus 2. That is 3. The elements are from R. We need to take care of that one. So 1, let's consider 1, 1, 0, 2, and then 0, 1, 2, and 1. This is equals to, let us multiply them. So 1 into 0 is 0 and then 0. So of course from very first entry it is evident that these two not equal because two matrices A and B are equal if and only if the corresponding Aij equals to Bij for all I and j. So this is the case, but let us write this product. So 1, here comes 4, second one is 1 plus 1 into 1, 1 into R into C, 1 into 1, 1, and then plus 2, and then this increase. This is 0 and then 4. This is 4 and then here 3. So what we see, AB is not equals to BA. So this is the example. There are many examples we can take. To show this result, that AB is not equals to B. So with this, I will stop today. In next videos, I will be discussing more solutions and more questions from the exercises of your textbook. Thank you very much for watching.